Hello, so today we are doing this problem called k closest points to origin, and the problem says we get a list of points on the plane, and we want to find the kth closest points to the origin, which is 0, 0. And the distance here between 2 points is just the Euclidean distance between them, which is just the basically the difference between the x squared plus y squared of the point minus the ones for the origin. So that's what we are looking for. And so we might return the answer in any order. It is guaranteed to be unique. And so, for example, for this here, 1, 3 and minus 2, 2 and k equals 1 means we want the closest, just one closest points to the origin. So the distance between 1, 3 and 0, 0 is the square root of 1 squared, which is 1, plus 3 squared, which is 9, so 1 plus 9, so it's the square root of 10. The distance between this one and the origin is the square root of minus 2 squared, which is 4, plus 2 squared, which is 4, so 4 plus 4, 8, square root of that is 4, right? And so comparing these two, this one is smaller, so this one is closer to the origin than this one. And so this one is the answer. And so we want the closest, that closest point, and so the answer is just that. And the similar thing for the second example. So how can we solve this problem? So the first thing we can think of is let's just sort them and take the kth first element, pretty much. Let's just calculate the distances, sort them, and take the kth smallest ones. That's the first straightforward solution. So let's code that one up. So first we know we need the distances, right? And so let's just construct the array of that. So that would be if we can just use this list comprehension in Python, and we need the square root of, so I need to import math to get the square root, and so that would be just applying the formula for the Euclidean distance, so square root of p0, or maybe let's just say xy, right? So and then so this one x squared plus y squared, and square root of that. And what we want to do is sort this, and what should be the key? So we want, let's call this distances first. So this is distances, right? And let's just make this a pair so that we can get because what we want is to return the point at the end and not the distance. So we need to keep track of the points. So the point would be, then let's just do p, so that we can do p here, and we can do here, that's p0, and this is p1. And once we have that, we can just sort it. So sort distances by key, which would be, so the key would be the first value, so that's x0. That's just the default value anyway, so we can just leave it like this. And what do we want? We want to get the k smallest ones. And what do we want from that? We want the points, not the values, not the distances. So we need to create a list comprehension of that, and just say, let's take points for, so we get distance and p in this list, right? And then we can just return that. And so for each one we have the distance and the point, right? And then we are interested only in the kth smallest, and when we sort, the first k elements would be the smallest, right? And so let's just run that. So it's actually sorted like this. Okay, so that seems okay. Let's submit. Cool, so that passes. So this is the straightforward solution. Another way to solve this is using a heap, a min-heap. So we can use a min heap where we put the distances. So we put all the distances, d1, d2, all of them with the points, of course. Let's say as pairs. Like this. And then we can go through the min heap, and take and pop k times, because each pop from the min heap will give us that's the smallest element, and so when we pop k times, the result is what we are looking for, is the answer, right? Because let's say we put in our min heap here, let's say we put an element, let's say a point that is like has distance 2 and it's point p1, the other one has distance 3, it's point p2, the other one has distance, let's say 1, and it's p3, and the other one, let's say 5, and it's p4. Now let's say k is equal to 2, so if we pop k times, we will get the first one we will get is the smallest distance, so that's p3. The second one we will get is 2 p1, and we will be done, and that's the answer, because if the min heap will get us always the smallest element first, the smallest by the first element, which is the distance, right? And so that's pretty much what we will be doing here. And so we need our heap, and we need to go through the points and add the and so the way we add is we need to import heap q, and so we need to do this and push distance and the points, right? So we know we need points, and then we know we need map that square root of 0 squared plus p1 squared. And once we get that, and we push that, we need to push that to past the first element that we are pushing to, and pretty much that's what we will be doing. Now the result that we are looking for is just, as we said, popping k times, right? So what we'll do to get that is say while k is bigger than 0, every time just pop and append that to the result, which means we'll do heap pop the smallest element by distance, and then we say, okay, we already had one, we extracted one, and so subtract k, and when it reaches 0, that means we have all the smallest or the closest points, right? And so we can just return that result. Okay, so here there's something wrong with the parentheses, so that should be it. Okay, so we have a problem here because of the distance is returned in the response, right? So what we want here is not get the distance, we just want to get the points, right? So we need to do 1 just to get the points, which is at position 1. Okay, so that should work. Let's see. Okay, so that passes. And so with heap sort in Python, it can be done in a more efficient way, which is, or like shorter way. So instead of doing this, we can just use heap q has a method called n-smallest. So if I go here and say heap q to see the documentation, let's import it first. So you can see it finds the n smallest elements in the dataset, so the k smallest ones. And so let's just take that one and say, so what are the parentheses you need to give? N first, and then the iterable. So our n value is k, and the iterable is the distances, right? So we need to construct that distance. And then we can give the key. So we can either convert points into a pair of distance point list, or we could just pass points and make a custom key. So we can just pass points like this instead and make a custom key, which is a function that will get given the point, and our key would be the distance, right? So that would be square distance to origin, and from that point to origin. And so this would be square root of p0 squared, right? The same thing as we did before, plus p1 squared. P1 like this, and that's pretty much it. And this will give us the points. We don't need to do anything else because we didn't change this list. I didn't return it, sorry. Okay, so now let's submit this to make sure it works. Okay, solution passes. Now we can try to do another method, which is using Quickselect. So let's do Quickselect. So for Quickselect, we can just, I have a video on explaining Quickselect. It will be useful if you watch that first, but the main idea is we will partition the list into smaller and bigger values, and then we will keep iterating until we know we have all the k smallest on the left, and we just take these. That's essentially the main idea. And so the first thing we need is the distances. So let's just call them Euclidean distance list or something like that. And we will just calculate a pair of distance and points. And so that would be P0, same thing. We need so we can either use square root or just leave out the square root, because if it's closer using just the distance, then it's certainly closer if we use the square root, right? So we can just do this for now, and we can try later with square root. And then we need the point itself, and this is for the list of points. Okay, so after that we need to define our Quickselect method that will take the values that we want to select in, and the boundaries left and right, and how many we want to select, right? And so we will do usually here the template for Quickselect, but what we need to return is so what we will be doing is we want to do Quickselect for that including distance, right? So that's this one, and we want to pass as the start point the first element, the end point is the last one, and we want k elements. And the other thing is that what do we want to get at the end? If we do this, we will get the pair, but we want just the point. And so let's just say we are going to get let's call this element 1, so that will give us the point for, or let's say this E1 for E in Quickselect, like this. But The other thing is that since k here is numbered from 1 but our list is numbered from 0, we'll need to say -1 here, right? And also Quickselect usually doesn't return anything, so that's the usual template for Quickselect, but it will convert the inclusion, the list that it will be given, it will convert it in a way that the first k elements would be the smallest ones, and then you would have another set. So this, our inclusion list here, will end up being like this. So it will not sort the entire list, but it will give us the k smallest elements in this on the left side, and the rest we don't care about it. But we know it's not, all of it is bigger than the k elements here, And so once we do this, we know that that's the property that Euclidean list has, and so we could just use that and take the k elements on the left, which we know are the smallest ones, and just pick the points there, right? And so that's pretty much what we need to return. Now let's do our Quickselect template. So we need to check if our base case, if we have only one element left, then the result in that case is just return. We don't need to do anything else. And otherwise, we need to do the partition, right? So we will get the pivot index, and we will call a subroutine called partition, where we give the left and the right values. So this is partition, it's back values, left, right, and we will need to give a pivot to the partition. We can choose anything as the pivot index, right? Let's call it pi. But in my case here, I'm just going to return k as the pivot. You can do whatever. You can return the right. You can give the rightmost element, the leftmost element. The pivot does matter in some cases, but overall, for our sake here, it doesn't. And so we can make that the pivot index, and we'll do the partition code later. But right now, if the index is, if k is less than the pivot index, where we're partitioned at, that means for a case like this, let's say, and we have our pivot here, and let's say the pivot is, for example, I don't know, any number, let's pick 8, right? And let's say k looks for the four closest points. Then we know that there is no need to look here, because all these are bigger than p, right? And all these are smaller than p. So certainly we should look at this section, right? And so to look at that section, we need to say recurse on Quickselect values, and our left side stay the same, right? But our right side becomes p-1, right? Otherwise, if it's on the right side, then we need to so it's on the right side. Let's say k was 11, right? So we know we need to look at this, right? And we know this one we want to take anyway, right? So, but we know we need to look at this to get the rest, right? And so we need Quickselect again on values. So this would be and the start point will be p+1, and the end point would be still the same, this right position here. So we need right, and k, we are still looking for k elements, right? So one thing you may wonder is, why didn't I do k minus p, right? So I would have done that if I was passing a shorter list. Let's say I was passing p+1 to error here, but that's not what I'm doing. I'm keeping the boundaries using just left and right. So the partition index would be still telling me something in between these two, because I'm using left and right, right? And so for that reason, I would have to pass in just k. Now let's do the partition step. So the partition step needs to have basically needs to put all the elements smaller than the pivot to the left and all those bigger than the pivot to the right. So I'm just going to have this store index that kind of just marks where I'm at. So basically while I'm doing the partition step like this, so I'm doing the partition step, I found an element smaller, I need to move it here. But where do I know where to move it? I need an index that tells me you can move it here, right? You can move it here. And move it here means basically I will swap this element, which is x, with the element that I found that is smaller here. And basically store kind of tells me these are all smaller than the pivot, because store starts out on the left side and and then when we find an element that is smaller than the pivot, we will put it at this position of store and move the store. Then when we find another element, put it at the position of store, move it again. And that's what partition does. And so we need to keep track of that, and it starts out on the left. The other thing that we usually do with Quickselect and Quicksort is that the first thing we do is we move the pivot to the right position. Then, so this is the right position. Then what we do is we keep putting elements that are smaller than it on the left. And when we are done, and there is no more small elements smaller than the pivot, we come and we put the pivot here so that it serves as a limit between the smaller than it and the section and the bigger than it section, right? So this would be smaller than the pivot section. Just give it more elements. So this section would be smaller than the pivot, and this section would be bigger than the pivot. And so we need to do the swap that I just said, so that sorry about that. So that it's so we need to have so we need to do this partition this way, and we need to have the pivot on the right side, so that at the end, once we go through all elements, we can put the pivot at the store position. And so to do that, we'll start with store on the left, and then we need to swap the pivot, because we don't know where the pivot index was set to. So to do that, we will say pivot index, swap that with the right position. And then we will start going through the list so that we can put all the smaller elements than the pivot to the left and all those bigger to the right. And so for that, we'll say in range of left and right, we'll check if nims of I is less than nims of right. So our pivot is now at right, so at the right position, so we need to compare against that. And if it's smaller than the pivot, then we need to swap it with the store position. Remember, that's where we last put the last smaller element. And so the last smaller element is just before the store position. And so we need to put the new one just next to it. And so to do that, we'll just say store nims of, this time is I, and we will swap that with this. And once we do that, we will need to move store so that the next element can be put in that position, right? And so we'll say store +1. And now at the end, we'll need to swap store with pivot so that pivot kind of stands between those smaller and those bigger, right? And so because all those smaller we put in positions on the left of store, right? And so when we put P here, then we are sure we have only smaller than P here and only bigger than P here. Because if there was one smaller than P here, we would have swapped it with something before the last position of store, right? And so we will need to say nims of store and nims of right and nims of right, because right is the position where we swapped the pivot, right? And so at the end, we know that the pivot position is store because we just swapped it, right? And that's pretty much it. But you can notice here I used nims, but that's not really what I should be using. It's values. That's what we are using here as our list. the other thing is that I can't compare them. It's a pair, right? It's a pair of distance and point, but I should be comparing against its distance. So an element is considered, a point is considered closer to the origin than the other one if the distance is smaller. So I should compare the distances here, right? But all the rest stays the same. And so you can see here, this is good insight in that Quickselect doesn't always have to be number less than number. It can be any expression that will help you decide whether an element is smaller or not than another element, so that you can partition using this this method here, right? And so that's pretty much it. We have our Quickselect, we have our partition step. Now let's just run this. So there is a syntax error on this line. Yep. Yep, we need to pass K. Okay, so that looks reasonable. Let's see for this example. So it's that, and it's 2. Let's run this. Okay, I'll submit. Okay, so this solution passes to using Quickselect, and the time complexity of the sort methods that we did earlier, that was O van Lagen. For the heap method, it's also O van Lagen, O of K Lagen, sorry. And then for this one, it's the usual complexity of Quickselect, which is time complexity is O van in the best case, or the average case, but it can degenerate to O van squared in the worst case. For the space complexity, that's just here. It's just I'm doing the recursive calls, but I'm doing them only at most n times, because I don't recurse on the 2 sides at once. Every time I recurse only at the left or on the right side. And so it's O van also in the average case, but can become O van squared if we have a really bad pivot selection choice. Yeah, so that's it for this problem. Thanks for watching, and see you next time. Bye.